In this video, we're going to be looking at composite functions, and we're going to look at the notation that we use and look at some familiar examples. Before we do that, though, I want to look at this slide on the summary of the domain and range work that we've done. So for very common functions, it's important that you know the usual domain and the range of these functions as well. So starting with x squared, what we can talk about for x squared is the natural domain. And what I mean by that is it's the largest possible set of real numbers that can possibly go into this. All right. So seeing as nothing really goes wrong with x squared, the natural domain is the real numbers. Okay, I'm going to use the pen actually. So what that is, it's largest possible subset of the real numbers, which in this case is the whole thing. Okay, so that's the natural domain. The range of x squared, what possible outputs can we get? Well, that's anything that's not negative. All right, so any non-negative number. Okay, greater than or equal to 0. Right, okay, there we go. Domain and range. For 1 over x, something goes wrong with 1 over x. We can't have 0 in our function. So the natural domain this time is the real numbers except for 0. Okay. There is a more concise way of writing this down. If you want to use set notation, I can put real numbers and then minus, so throwing away the set containing 0. Okay, that's just the same way of saying the same thing. The range of the function, I can get anything out of this except, again, for 0. So the range is the same. So I could say r minus 0 again. Or to stick with our f of x notation, we can say, f of x is not 0. There we go. Okay, ln of x. We've seen log graphs before. We know what the shape is, and we know that we have to restrict the domain a bit more heavily this time because our input in here can't be negative or 0. So our domain this time is positive real numbers. There is a concise way of writing this one as well. We can say real numbers, but then this plus means just the positive ones. So that's handy to know that one. The range, if you think about the graph of ln of x, you can actually get anything out of that, any output you like. So the range is just r, okay, or the real line, because you can get anything from minus infinity to infinity. E to the x, though, that has no restriction on its domain. The domain is real numbers, but the outputs this time have to be positive. So the range is positive reals, or you can just say f of x is greater than 0. Okay, and then you might have spotted the link between these two. These are inverse functions, and you'll notice the link between the domains and ranges. Okay, we are going to cover that in a separate video. Finally, this quadratic here, we can work out the domain and range again. Now the domain it's a polynomial function. Polynomials don't have much that can go wrong with them in terms of inputs. So real numbers is the inputs there. But the range, because it's a parabola, it's going to have a restriction on the range. And to work that out, we need to ideally know where the turning point goes. So if we complete the square, then 1 squared is 1. I need to get to 9, so you add 8. That gives us more of an idea of the range because 8 is the minimum point and anything else is going to be 8 or greater. So f of x is bigger than or equal to 8. The set notation way of writing that down is we can say 8 is the lower bound with a closed bracket, a square bracket I should say, and then infinity is the upper bound. So that's kind of the interval way of writing that down. Okay, this one hasn't got a natural domain. It's had its domain restricted from -1 to 4. It's still x squared. If you want to work out what the range is, you need to be quite careful. It's useful to know what happens at the endpoints, but that doesn't always give you the full picture. So -1, if you sub it into your function, then you can get out 1. If you put 4 into the function, you get 16. So you might be tempted to think that 1 to 16 is the range of this function, but it's not, because if you plot the graph of x squared, then you get -1, 1 up here, and then you get 4, 16 somewhere up here. But if you plot the function, it actually doesn't go between the two. Okay, it actually goes from 0 to 16. So that's our range for that one. So 0 less than or equal to f of x less than or equal to 16. So drawing the sketch, if you know what the shape looks like, gives you more of an idea of what's going on in between, even though the endpoints are important. The interval way of writing this down is square bracket 0, 16, square bracket. Okay, so that's just a summary of the domain range work that we've done. Okay, just bear those things in mind. All right, next then, if I move on to composite functions, I need to get rid of this with my new gadget. Perhaps not. Okay, composite functions. You've probably seen this diagram before to help explain it. It's where you apply functions in succession and put one function into another. So starting on the left with x, then that goes through the function f to produce f of x as the output, and then the output goes into g, and that makes g f of x. Okay, and the way that you'd normally see it written is like that. You sometimes see it with brackets this way. That makes it a bit clearer what goes first. A third way you might see it, which it doesn't happen that often at A level, but you sometimes see a circle instead of just nothing there. So G circle F. This is just the composition symbol. Okay, it's the composing function symbol, which you might see at some point. Okay, so F goes first, then G. The resulting function is GF. The way I was taught to think about what goes first is a bit like a rugby scrum. So if X is the ball, and you've got all these players fighting over the ball, then the one closest to the ball is the one that gets first touch, if you like. So F is closest in, that goes first, G goes second. Okay, so let's see some examples, shall we? Okay, so two functions. F of x is x squared plus 1, g of x is 4x minus 2, and I want to kind of compose them in these kind of ways. So fg of 2, well, we've said that the closest one in goes first, so I want to do g of 2, and then the output for that goes into f. That's not working. Okay, so g of 2 goes first. G of 2 is 6, because it's 8 minus 2, and then 6 goes into f, and that comes 37. Fg of x, if I want that just as a function of x, then you can do something similar. So g of x you look at, and then all of this then goes into f. So let's highlight that. That's my output for g. It goes into the input for f. So you kind of squeeze that into the x, and it becomes a new function by itself. So that's what we get. This line in particular, 4x minus 2, that's the input. You square it and you add 1, and then if you want to, you can expand it out. Okay, so it says any instance of x in the outer function, it gets replaced with the inner function. So 4x minus 2 went in there. If you swap them round, it's different. So this time the x squared plus 1 goes into that x there. Come on. There we go. Right, this is my inner function. It goes into the outer one. It goes into that x there. So it's going to this time be... Oh, no, come on. This one, okay, 4 times, and then x squared plus 1 minus 2, which you can then tidy up if you want to. Okay, and notice that these things are different. Okay, if you swap the order of composition, then in general it's not the same. You might want to think about actually as a little bit of an extension, what kind of functions can you think of where if you swap the order around, these actually would be the same? Okay, what functions do that? Okay, f squared of x, the power in the middle is repeated composition. So there you go, f squared of x, it just means f of x. You apply it twice. So this time x squared plus 1 comes out, it goes back into itself, so then it looks like this. Okay, f of x is you take the output, you square it again and add 1 again. Okay, so that kind of makes sense as a notation because it's like repeating itself. That then makes it consistent with the inverse function notation, right, which you would have seen. So if you do f minus 1 of x, that's the inverse. And you should think of it as like applying f minus 1 times. Okay, you go backwards by an f. Okay, so it kind of makes sense if you think of it like that, even though it's not really a reciprocal. So with that in mind, then you might want to think about, okay, what about f0 of x? Can you make sense of that? For any function f, what is kind of the 0th power of it? Okay, is there a function that kind of makes sense of that? Okay, I'll leave you to think about it. All right, solve gf of x is 38. We've already worked out gf of x. It's 4x squared plus 2. Hopefully these should be nice and simple things that you can then put into an equation, and then you solve it equaling 38 and you work out x. Okay, nice and easy. So take away 2, divide by 4, square root, and you get plus minus 3. Okay, so that's using the functions. Shouldn't be new stuff for you. It should kind of be familiar to you. We'll look at some functions though that have kind of reasonably new. These modulus functions are quite new, so we'll have a look at them as well. Fg of 3, so g goes first. You put 3 into g, and it looks like that's going to be 2 comes out. Then 2 goes into your f, it goes into the modulus, 4 minus 8 inside, makes minus 4, and take the modulus of that and it makes 4. Okay, fg of x equals x, so I want a function of x for that. All of this goes into your modulus, so g goes first, put it into the x for f, that's how it looks. Tidy it all up, the 2 and the 2 cancels out, and you get x minus 7 in your modulus. I want that to equal x, and then that's just the thing that we did last week. Okay, so you plot your x minus 7 modulus function, you plot y equals x, and it looks like you get a single solution. And you get your solution on this negative branch. This left branch is 7 minus x, okay, or minus x plus 7. So you solve that and you get 3.5. Okay, hopefully still nice and easy. There's a couple of examples here that you might want to look at. I might go through the first one just to kind of get used to using this kind of stuff, but it's all pretty much the same. I'll leave it to you to have a little look. All right, so f is this function here, 2 times the mod of x plus 3. G is 3 minus 4x. Both real numbers for the domain. Fg of 1, I'll do that myself without uncovering the box. So f of g of 1, well, g of 1 goes into g, you get 3 minus 4 is minus 1. Then 2 times mod minus 1 plus 3 is 2 times 1 plus 3, which is 5. Okay. Solve the equation g of x plus g of x squared is 0. Notice that these two things aren't actually the same. Okay, this is repeated composition, and this is actually squaring the output. Okay, which isn't the same. So let's do g of x first. So that's 3 minus 4, and then instead of x, I've got all of g again as well. So 3 minus 4x. Okay, what's that? 3 minus 12. Plus 16x, which is 16x minus 9. G of x squared helps to have these square brackets to kind of really make it clear. I just need to square g of x, 3 minus 4x, all squared. Okay, add these up, make it equal to 0. So 16x minus 9 plus 3 minus 4x all squared equals 0. Now I'm going to use this space. So 16x minus 9 plus, expand the brackets, 9 minus, it'll be minus 24x. Will it? Hang on. 8, yes, 24, and then plus 16x squared equals 0. Tidy up. Okay, how many x's? 16x minus 24 is minus 8. Minus 9 plus 9, and that looks like that's it. Divide by 8. Factorize. And get your solutions. X equals 0 or a half. Okay, there we go. I'll leave you to do this one. Fg of x should be something quite nice if it's e of x, ecx and ln of x, but I'll leave you to have a look at that. And that's composite functions. Okay, those are the kind of questions that you tend to get. Make sure you put things in the right way around and you're able to sub one function into another properly. Okay, and do some casting out and simplifying. Okay, best of luck. Well done, Year 12. I'll see you soon.